Over the next 50 minutes, I will take you deep into the hearts of the most extreme celestial bodies in the universe. You'll witness the astonishing forces that emerge when matter is subjected to nearly infinite pressure. Are you ready? Let's begin our journey. Inside stars, the continuous buildup of magnetic energy can trigger massive solar flares that erupt with violent force, spewing streams of energy into the frigid void of space. Far away, a distant supergiant begins fusing iron at its core, setting off a chain reaction that culminates in a spectacular supernova explosion, tearing the star apart from within. Elsewhere, within a rapidly spinning magnetar, increasing internal pressure causes starquakes on its surface, unleashing powerful gamma-ray bursts. These phenomena are all examples of the universe reaching its critical points, moments when delicate cosmic balances are suddenly broken, leading to dramatic transformations. The matter that forms planets, stars, galaxies, and even ourselves appears stable. Yet in truth, it all teeters on a knife edge of equilibrium. From the tiniest atom to the vastest supercluster, everything exists in a subtle balance. But once any system crosses a crucial threshold, chaos inevitably follows. And yet, amidst the chaos, there is often hope. At subatomic levels, a hidden safety net frequently springs into action, restoring balance and preventing complete annihilation. Nowhere is this paradox of destruction and stability more evident than in the core of a neutron star. A neutron star is the universe's final barrier before total collapse. A celestial object so extreme, it may well be the most extreme in all of space and time. These tiny, unimaginably dense remnants of dead stars spin at dizzying speeds. Their very existence defies the limits of known physics. The gravity on a neutron star is so intense that mountains can rise no more than a millimeter high. Anything falling toward its surface would accelerate to half the speed of light before making contact. And yet, as we probe deeper into their ultra-dense interiors, we find conditions growing even more extreme. At their cores lie strange secrets, where matter is crushed under pressures unmatched anywhere else in the cosmos. These conditions could force us to rethink everything we thought we knew about the universe. Neutron stars are the ultimate laboratories of physics, pushing ordinary matter to the brink of annihilation. To understand the inner structure of a neutron star is to uncover the true nature of reality itself. So before the universe collapses in on itself, the question remains, how far can we push the limits? On December 24th, 2024, while people on Earth celebrated the festive season, the Parker Solar Probe was setting new records in the far reaches of space. Traveling at a staggering speed of 200 kilometers per second, it flew closer to the Sun than any human-made object before. It entered an orbit just 6 million kilometers from the Sun's blazing surface, a distance that allowed the probe to pass through the Sun's outer atmosphere, known as the corona. This corona is a veil of incredibly thin plasma, from which the Sun launches powerful coronal mass ejections, massive subatomic bombs as vast as mountains. Once these ejected materials reach Earth, they can disrupt the planet's magnetic field, potentially causing widespread power outages. So now let's trace the source of such immense energy. Beneath the Sun's surface lies a thin layer called the chromosphere, with temperatures around 5,000 degrees Celsius. Descending further, we reach the visible surface of the Sun, the photosphere. The photosphere is constantly churning and boiling with activity, as searing hot material from the immense furnace below surges upward. It is a truly awe-inspiring sight. To fully understand the nature of this extraordinary environment, and to grasp how the Sun's inner structure connects to the mysterious core of neutron stars, we must travel back over a century. In 1923, Indian astrophysicist Meghnad Saha introduced the Saha ionization equation, a groundbreaking formula that describes the physical and chemical conditions within stars. Using this equation, astronomers can determine the degree of ionization in different layers of the Sun based on local temperature and pressure. From that, they can infer the state of matter present in each region. In physics, ionization refers to the process of breaking atoms apart, pushing them to a critical threshold. In a simplified model of the atom, negatively charged electrons orbit a positively charged nucleus, much like planets revolve around the Sun. Though the analogy isn't perfect, it helps to visualize the structure. An atom is electrically neutral because the opposing charges of the electrons and nucleus cancel each other out. These opposite charges also generate an attractive force that keeps the electrons bound in their orbits. However, when energy, such as heat, is supplied to the electrons, they can gain enough energy to break free from this subatomic grip. Once that happens, the electrons are liberated. In the language of physicists, the matter has been ionized. The result is a hot, electrically charged soup of free electrons and atomic nuclei, what we call plasma. In school, we learn that matter exists in 3 states: solid, liquid, and gas. But that's not the whole story. Plasma is the 4th state of matter, and it's the most crucial state found at the core of neutron stars. According to the Saha ionization equation, even though the sun's photosphere burns at roughly 5,500 degrees Celsius, it's still not hot enough to strip every electron from every atom. Instead, the photosphere exists in a partially ionized state, a mixture of hot gases and plasma. To find a region where plasma truly dominates, we must go deeper. There, the temperature climbs to at least 10,000 degrees Celsius. Once we reach about a quarter of the way into the sun's interior, we arrive at its core, a realm of extreme density and unimaginable intensity. Here, the colossal weight of all the sun's upper layers presses downward with astonishing force. The pressure at this depth is 250 billion times greater than the atmospheric pressure at Earth's surface. Plasma in this region is compressed to extraordinary density, up to 150 grams per cubic centimeter, nearly 8 times the density of gold. And yet, despite this immense compression, the sun's core is primarily composed of the lightest element in the universe: ionized hydrogen. Just a single tablespoon of this core material would weigh between 5 to 8 kilograms. If you were to fill an Olympic-sized swimming pool with it, the total mass would exceed that of the Titanic, passengers and cargo included. Naturally, if gravity were left unchecked, the sun's core would be unable to withstand such immense internal pressure and would ultimately collapse. But that is not what happens. Instead, the sun remains stable, delicately maintaining an invisible internal balance that has lasted for billions of years and will continue to do so for billions more. So what force prevents the sun from crossing this critical threshold? At the core of the sun, hydrogen atoms are compressed so tightly that they fuse into helium atoms through nuclear fusion. Every second, about 620 million tons of hydrogen are consumed, while 616 million tons of helium are produced. The missing mass is converted into energy. This means that each second, the sun releases the energy equivalent of 4 million tons of sunlight. However, because the sun's density is so high, it takes the average photon around 170,000 years to escape from the core and reach the sun's surface. The outward pressure generated by this nuclear energy, combined with the searing heat at the core, serves as the only counterforce preventing the sun from gravitational collapse. This delicate balance between outward thermal pressure and inward gravitational force is known as hydrostatic equilibrium. Physicists and astronomers use the equation of state to calculate and understand this balance. The equation of state describes the intricate relationship among temperature, pressure, and density at different layers within a star. A softer equation of state results in a more compressible core, while a stiffer one provides greater resistance to gravity. Remember this concept. The equation of state is a fundamental pillar for understanding how neutron stars operate at their core. What's remarkable is that, although astronomers cannot directly observe the sun's core or get close to it, they are still able to estimate the sun's internal equation of state with impressive accuracy. This insight has been made possible by one particularly elusive subatomic particle, the neutrino. As the sun fuses hydrogen into helium, it produces an enormous number of neutrinos. In fact, around 1.79 non-alien, that's 1.79 followed by 30 zeros, solar neutrinos are generated every second. These neutrinos stream out of the core and flood the entire solar system. If you hold your hand up to sunlight, more neutrinos pass through your thumbnail in a single second than the total population of Earth. Over your lifetime, the number of neutrinos that will pass through your body is roughly equal to the number of stars in the observable universe. Yet the number of neutrinos produced in the sun's core is highly sensitive to local conditions. especially temperature. Even a slight change in core temperature causes a dramatic shift in neutrino output. This makes solar neutrinos the perfect thermometer for measuring the sun's interior, which scientists estimate to be about 15 million degrees Celsius. Understanding the sun in this way is crucial, and its implications are far-reaching. The sun is the closest star to Earth, about 2.65 million times nearer than the next closest star. While astronomers have studied other stars through a technique called astroseismology, none have been analyzed in as much detail as our sun. As a result, the sun and its equation of state serve as a benchmark for measuring and modeling all other stars in the universe. It is the ideal starting point for understanding how the equation of state changes when stars die. And though the sun may continue balancing on the tightrope of hydrostatic equilibrium for billions of years to come, in the vast timeline of the cosmos, every entity, including the sun, must eventually meet its end. Even stars are no exception. The sun, like all stars, will one day exhaust its core fuel. When that happens, nuclear fusion will cease forever. What follows is destined to be nothing short of astonishing. In some stars, this final, catastrophic transformation gives birth to something truly extraordinary, beyond the bounds of conventional understanding. Ralph Fowler, once a mathematician at Cambridge University, redirected his focus from pure mathematics to physics during World War I. His pioneering work laid the foundation for a Nobel Prize-winning breakthrough in astrophysics. This discovery revealed that one of a star's critical thresholds could, in fact, be crossed, placing matter into an entirely new and far more dangerous realm of subatomic equilibrium. At the heart of this revelation was the inner mechanism of a very special kind of star. On winter nights in the northern hemisphere, a dazzlingly bright star dominates the sky. Not only is it the brightest star in the night sky, but it also twinkles with vibrant, shifting colors. This is the famous Sirius, the primary star in the constellation Canis Major. Throughout human history, Sirius has held deep cultural and astronomical significance, especially when it rose in conjunction with the sun and temporarily vanished from the night sky. But Sirius is not a solitary star. It is part of a binary system, accompanied by a fainter companion, Sirius B. The two stars orbit each other once every 50 years. For several years after World War I, the true nature of Sirius B remained a perplexing mystery. On one hand, it was smaller than Earth, yet somehow hotter than the sun. In 1922, Dutch-American astronomer Willem Jacob Luyten gave a name to this strange class of stars, white dwarfs. But what exactly are white dwarfs made of? One thing is certain: to compress the mass of a star into a space no larger than a planet requires unimaginable. A single cubic meter of white dwarf material weighs about 1 billion kilograms. A chunk the size of a sugar cube would weigh as much as an elephant. A single shipping container filled with white dwarf matter would rival the mass of the Great Pyramid of Giza. By ordinary logic, such a dense object should collapse under its own gravity. In the sun, it is thermal pressure produced by nuclear fusion that resists gravitational pull. But in the far denser white dwarf, thermal pressure alone is no longer enough. So what force is preventing Sirius B from collapsing? The answer came from Ralph Fowler, along with his colleague Arthur Milne and the legendary astrophysicist Sir Arthur Eddington. They discovered that the interior of a white dwarf consists of degenerate matter, a concept emerging from the revolutionary physics of the 1920s. It was a golden age of discovery, as scientists began to unravel the far-reaching consequences of a new branch of science, quantum mechanics. This was the era of Schrödinger, Heisenberg, Bohr, and Pauli, giants whose work reshaped modern physics. And it was Pauli's exclusion principle that provided the key to understanding degenerate matter and ultimately the true composition of white dwarfs and neutron stars as well. Quantum mechanics earned its name because in the atomic realm, only specific quantities, quanta, are allowed. Subatomic particles can only occupy discrete energy levels. When particles share the same energy, they must differ in some other quantum property to remain distinguishable. Otherwise, two identical particles with the exact same properties cannot coexist in the same quantum state. The number of alternative quantum properties that particles can possess is limited. This means that within each permitted energy level, space is also limited. To understand how this works in practice, imagine a skyscraper where each floor represents a quantum energy level that a particle is allowed to occupy. Here's the key. Just like a real skyscraper, each floor has a legally enforced maximum capacity. Any additional people attempting to enter a full floor are simply turned away. This is the essence of the Pauli exclusion principle. For example, inside the sun, particles are dispersed sparsely enough that these capacity limits are never a concern. But when matter is compressed to the extreme densities found inside a white dwarf, things change. The lower energy levels quickly fill up. Then the first level above and the second. No matter how hard gravity tries to force more particles into the lowest available states, the exclusion principle pushes back with growing resistance. This quantum mechanical resistance is known as degeneracy pressure. Today, we know that white dwarfs form at the end of a star's life, particularly in stars like our Sun. When such a star dies, roughly half of its mass is compressed into an ultra-dense white dwarf. The other half is shed, expanding outward in a complex and spectacular display of glowing gas and dust known as a planetary nebula. In fact, about 7 billion years from now, our own Sun will share this very fate. However, for stars more massive than the Sun, the endgame might look drastically different. Let's return to the night sky once more. If you trace a path upward and to the right from Sirius, you'll soon find the iconic trio of stars in Orion's belt. Continue along that same line, and you'll encounter a star cluster shaped like the letter V, the Hyades cluster, part of the constellation Taurus, marking the bull's head. From each tip of the V, 2 horns rise. Near the top of the left horn, close to the star Zeta Tauri, lies one of the most famous gas and dust clouds in the sky, the Crab Nebula. It is the remnant of a massive star that once burned with unimaginable intensity. In the year 1054, during the Northern Song dynasty in China, official astronomers recorded a sudden, brilliant guest star appearing in the sky. It was so bright that it remained visible even during the day for nearly 2 months, and lingered in the night sky for a full 2 years before finally fading from sight. To call it a supernova almost doesn't do justice to its sheer power. In just a few seconds, a supernova releases more energy than our Sun will emit over its entire multi-billion-year lifespan. And these events are not as rare as one might think. Astronomers estimate that somewhere in the universe, a supernova occurs roughly every 10 seconds, which means that since you started reading or watching this very segment, over 100 supernovae have already exploded across the cosmos. And yet, what lies at the heart of the Crab Nebula is perhaps even more astonishing: a neutron star. If the density of a white dwarf is already hard to fathom, then a neutron star takes it to an entirely new level, 100 million times denser. Just a single tablespoon of neutron star matter would weigh more than the total mass of all 108 billion people who have ever lived in human history. While a white dwarf is roughly the size of Earth, a neutron star is only as large as a city. The neutron star at the center of the Crab Nebula has a diameter of just 21 kilometers, about the size of London and slightly narrower than Tokyo. Yet more than the mass of an entire sun has been compacted into this unimaginably small space. As expected, the gravity of a neutron star is almost beyond comprehension. Escaping Earth's gravitational pull requires a speed of 11 kilometers per second. But the escape velocity from a neutron star is around 150,000 kilometers per second, about half the speed of light. On Earth, gravity is gentle enough to allow Mount Everest to rise nearly 9 kilometers above sea level. But on a neutron star, the tallest mountain would be less than 1 millimeter high, making these objects some of the smoothest bodies in the entire universe. And they spin at dizzying speeds. The neutron star in the Crab Nebula rotates 30 times per second, while others can spin hundreds of times per second. When a star goes supernova, it's not just its mass that gets compressed, its magnetic field is also dramatically intensified. A typical neutron star possesses a magnetic field that is 100 billion times stronger than that of a refrigerator magnet. This incredible field often channels beams of radiation from the star's poles. When these beams sweep past Earth, they strike us in rhythmic pulses, like a cosmic lighthouse. That's why we call these objects pulsars. One of the most critical breakthroughs came from Subramanian Chandrasekhar, who proved that Fowler's degeneracy pressure can only support white dwarfs with masses up to 1.4 times the mass of the Sun. This is known as the Chandrasekhar limit. If the core of a dying star exceeds this mass, gravitational collapse forces electrons and protons to merge, forming neutrons. This is how a neutron star is born. But even neutrons obey the Pauli exclusion principle, which means no two neutrons can occupy the same quantum state. As with electrons, this creates a natural limit on how densely they can be packed. Once an energy level fills, gravity can no longer compress the star further. This neutron degeneracy pressure becomes the last line of defense, the final critical point. It is the only force keeping a neutron star from collapsing into total annihilation, teetering just kilometers from becoming a black hole. Despite their name, neutron stars are not composed entirely of neutrons. In fact, the deeper we look into their interiors, the more mysterious and exotic their matter becomes. Much like the Sun, the surface of a neutron star merely hints at the extreme conditions lurking beneath. Our journey to understand the true internal workings of neutron stars has only just begun. Recently, a major clue emerged from a neutron star that theoretically should not exist. Aboard the International Space Station, a cutting-edge X-ray telescope called NICER, short for Neutron Star Interior Composition Explorer, has been collecting vital data that sheds light on the internal structure and exotic matter within neutron stars. Hovering just above the surface of a neutron star is a razor-thin atmosphere only 10 centimeters thick, made primarily of hydrogen and helium. And yet, its density rivals that of diamond. This ultra-thin atmosphere, hovering just above the surface of a neutron star, is heated to temperatures of around 2 million degrees Celsius. As we move deeper beneath this surface into the crust, the pressure becomes so immense that electrons are stripped from atomic nuclei, leaving behind a churning, ionized sea of electrons, protons, and neutrons. The crushing forces inside the neutron star's crust distort protons and neutrons into strange configurations never seen anywhere else in the universe. Physicists refer to this theoretical form of matter as nuclear pasta. Although its existence has not yet been confirmed through direct observation, its predicted properties come from highly detailed computer simulations of matter under extreme pressure. And if nuclear pasta does exist, it would likely be the strongest material in the universe, estimated to be 10 billion times stronger than steel. These simulations suggest that nuclear pasta can take on multiple structural forms, each one resembling a different type of Italian pasta. Near the surface of the neutron star, protons and neutrons may cluster into bubble-like formations. Astronomers call these gnocchi, named after the round, doughy Italian dumplings. As we descend deeper, the rising pressure squashes these gnocchi into elongated spaghetti-like filaments. Still deeper, the spaghetti compresses further into flat, layered sheets resembling lasagna. Altogether, these layers of nuclear pasta may only span a thickness of about 100 meters, yet their combined mass could exceed that of 3,000 Earths. For years, astronomers believed they had a fairly strong grasp of how neutron stars were structured. But in 2019, the universe presented them with an unexpected challenge. In theory, the most massive neutron stars should be the smallest in volume. Greater mass means stronger gravity, which should compress the star's matter into a tighter space. However, when astronomers used NICER to observe a neutron star designated J0740+6620, they discovered something puzzling. They quickly realized this was one of the most massive neutron stars ever observed, with a mass more than twice that of the Sun. By conventional reasoning, J0740 should also be among the smallest neutron stars. But it wasn't. In fact, its volume was comparable to that of other less massive neutron stars, despite having only about 2/3 their density. This revelation sparked immediate and intense debate. The very existence of this neutron star defied expectations. One possible explanation was that the equation of state astronomers had been using to model neutron stars was inaccurate. Unlike the Sun, whose internal equation of state is well understood, determining the equation of state for a neutron star is incredibly difficult. There are hundreds of possible models, and detailed observations are challenging to obtain. Moreover, we cannot replicate the extreme pressures and temperatures found inside neutron stars here on Earth. Yet J740 may help scientists narrow down the list of possibilities. Its unexpectedly large volume suggests that the matter inside may be less compressible, in other words, stiffer than previously thought. But there's another, even more intriguing possibility. This lack of compressibility might point to something far deeper. The enigma surrounding J0740 has led astronomers to re-examine what might lie at the very heart of neutron stars, beneath even the ultra-strong layers of nuclear pasta. Before J0740 stirred such intense debate, the mainstream view held that the core of a neutron star was a seething quark soup. Protons and neutrons, after all, are not fundamental particles. Each is made up of three even smaller constituents called quarks. As pressure in the core of a neutron star increases, scientists originally believed that protons and neutrons would be forced apart, disintegrating into their individual quarks. However, tearing quarks away from each other requires an enormous amount of energy, because they are bound together by the strongest known force in nature, the strong nuclear force. And here's the catch. If energy is being used to break apart these particles, then less energy is available to counteract gravity. According to this logic, the more massive a neutron star becomes, the more compact it should be. But as we've seen with J740, that's not always the case. To complicate things further, another type of particle has added fuel to the fire, the hyperon. There are 6 known types or flavors of quarks. Protons and neutrons are made from just 2, up quarks and down quarks. The other 4, strange charm, bottom, and top quarks, are typically found only in high-energy physics experiments. Hyperons are particles that include strange quarks but not charm, bottom, or top quarks. These particles were first discovered in cosmic ray experiments in the 1940s, but because of their extremely short lifespans, they vanished too quickly to study in detail. Some popular neutron star models suggest that the extreme heat and pressure in a neutron star's core might not only create hyperons, but could even allow them to remain stable for extended periods. But this idea comes with a serious issue. The presence of hyperons tends to soften the equation of state, weakening the star's ability to resist gravitational collapse. Instead of stiffening the core, hyperons would make the neutron star more compressible, not less. After the discovery of J740, the idea that neutron stars are composed primarily of quark soup, or hyperons containing strange quarks, suddenly became much more uncertain. But if we reject the quark soup model, what's left? If ongoing research continues to challenge the viability of quark-based models, then what exactly lies at the heart of a neutron star? One important factor that quark models usually don't account for is dark matter. Since the 1930s, astronomers have observed numerous cosmic phenomena that can't be explained by ordinary gravity alone, such as galaxies spinning too fast or gravitational lensing that bends light more than expected. One possible explanation is that the universe is filled with an invisible form of matter that acts as a kind of gravitational glue. The term dark matter was first proposed in a 1933 paper by Swiss-American astrophysicist Fritz Zwicky. Remarkably, just 1 year later, Zwicky, alongside Walter Baade, also proposed the existence of neutron stars. If dark matter truly exists, then massive stars traveling through the cosmos would occasionally pass through dark matter-rich regions. As they do, they could capture and absorb some of this dark matter, which would then sink to the core of the star. When such a star undergoes a supernova and collapses into a neutron star, the captured dark matter would remain in its core. Some research suggests that adding dark matter to a quark soup could stiffen the neutron star's equation of state, giving it more resistance against gravitational collapse. This could potentially explain why J740 is not as small as originally expected. But if this explanation holds, it would only require a slight adjustment to the quark soup model, not a complete rejection of it. There is, however, another theory, one that completely rejects the quark soup model. This theory, too, traces its roots to early 20th century India and to a physicist who worked alongside Meghnad Saha at the University of Calcutta, Satyendra Nath Bose. Together, they translated Albert Einstein's groundbreaking papers on relativity from German into English. In 1924, a conversation between Bose and Einstein sparked a new idea in Bose's mind regarding the behavior of certain subatomic particles. Struggling to publish his work in English-language journals, Bose took a bold step. He wrote directly to Einstein. "Respected Sir, I venture to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it." It was a daring move. Einstein not only responded but translated the paper into German himself and submitted it to a prestigious physics journal. Their collaboration gave rise to what is now known as Bose-Einstein statistics, and it predicted a completely new state of matter, the Bose-Einstein condensate. Today, physicists classify subatomic particles into two fundamental categories: bosons, named after Bose, such as photons, and fermions, named after Enrico Fermi, such as protons and electrons. The distinction lies in a quantum property known as spin. Bosons have integer spins, 0, 1, 2, while fermions possess half-integer spins, 1/2, 3/2, etc. This difference in spin has profound consequences. Spin is also associated with orientation, typically labeled as up or down. The Pauli exclusion principle, which we've previously discussed, applies strictly to fermions. No two identical fermions can occupy the same quantum state at the same time or place. This is why, for instance, two protons or two neutrons cannot be in the exact same spot. But in a Bose-Einstein condensate, all bosons can occupy the same quantum state. They move in perfect synchrony, as if they were a single unified superparticle. If bosons were to pair up in the core of a neutron star, and their spins aligned in parallel directions, they could potentially create a much stiffer equation of state. This would result in a stronger outward pressure, a new kind of safety net resisting collapse. This theory has led some astronomers to propose that ultramassive neutron stars like J0740, with at least twice the Sun's mass, might actually be Bose-Einstein condensate stars. Regardless of what J740 is made of, it remains one of the most massive neutron stars ever discovered. But that raises a new question. Just how massive can a neutron star get? What happens when it exceeds a certain limit? Is there another safety net to stop it from collapsing? The answer lies in a theoretical threshold proposed by physicists George Volkoff, Richard Tolman, and J. Robert Oppenheimer. This boundary is known as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit for short. Their initial calculations placed the maximum possible mass of a neutron star at about 70% of the Sun's mass, roughly half the Chandrasekhar limit for white dwarfs. But astronomers now believe this estimate was far too conservative. By the 1990s, as new models for neutron star equations of state emerged, astronomers revised the TOV limit significantly upward, placing it somewhere between 2.2 and 2.9 solar masses. However, to narrow down this range further, and to truly understand the final boundary between neutron stars and black holes, cutting-edge technology is essential. In the summer of 2017, the astronomy community buzzed with rumors. It all began on August 18th when astrophysicist Craig Wheeler posted a cryptic tweet, "New LIGO source with optical counterpart. This is unbelievable." Internet sleuths quickly jumped into action, combing through the public logs of major telescopes. They noticed that several observatories had suddenly redirected their focus, all pointing toward the same galaxy, NGC 4993, located approximately 140 million light-years from Earth. 2 months later, scientists officially announced the discovery. LIGO, the Laser Interferometer Gravitational Wave Observatory in the United States, had detected a signal that would go down in history. Two neutron stars had collided in the galaxy NGC 4993, unleashing a cataclysmic explosion. 70 observatories across all 7 continents and in space recorded the aftermath of this event. From LIGO's perspective, what was detected were gravitational waves, ripples in the very fabric of space-time, reaching Earth's cosmic shoreline. Just as swimmers, ships, and dolphins generate waves as they move through water, massive objects moving through the cosmos create waves in space-time. This marked the first time in history that astronomers detected gravitational waves resulting from a neutron star collision. As the two neutron stars spiraled toward each other and finally collided, the amplitude and frequency of the gravitational waves surged dramatically. Scientists carefully analyzed the data and ruled out several equations of state that didn't match the observed signal. This allowed them to narrow down the Tolman-Oppenheimer-Volkoff (TOV) limit, the maximum mass a neutron star can have before collapsing, to between 2.01 and 2.17 solar masses. Although some uncertainty remained, the result was a major breakthrough. On the other hand, another neutron star, PSR J0952-0607, is currently the most massive ever discovered, with a mass of 2.35 solar masses, seemingly exceeding the proposed TOV limit. However, as is often the case, the details are crucial. The basic TOV limit assumes a non-rotating neutron star, but most neutron stars rotate rapidly, and this spin can increase the maximum supported mass slightly. Still, the question remains, what happens when two neutron stars collide? In the 2017 collision, the total mass of the binary neutron star system was approximately 2.8 solar masses, clearly exceeding the TOV limit. Once this limit is surpassed, even degeneracy pressure is no longer sufficient to resist gravitational collapse. So what happens next? Before the material collapses entirely, could it reach another, even denser state of matter? This is still one of the most intensely debated topics in modern astrophysics. There are currently two leading possibilities. One is that neutrons are compressed so tightly that they dissolve into a sea of quarks, forming what is known as a quark star. Calculations suggest that an object made entirely of quark matter could remain stable. These hypothetical stars are sometimes called strange stars due to the presence of strange quarks. Appropriately, strange stars are thought to possess some truly unusual characteristics. If two quark stars were to collide, they might produce lumps of condensed quark matter known as strangelets. These strangelets could have masses ranging from 100 grams to 100 kilograms, and in astronomical terms, behave much like zombies. Strangelets are theorized to convert any matter they come into contact with into more strange matter. At one time, they were even considered potential candidates for dark matter, the mysterious substance that seems to hold the structure of the universe together. Although astronomers have never directly observed a quark star or a strangelet, it is still possible that these exotic forms of matter might reveal themselves in some other way. For example, deep within the permafrost of Antarctica, experimental detectors like IceCube might one day detect subatomic fragments produced when strangelets collide with Earth's upper atmosphere. However, if the neutron-star collision does not result in the formation of a quark star, then the only remaining alternative is the birth of a black hole. A black hole is formed when gravity surpasses the final threshold that even the densest forms of matter cannot withstand. At that point, the core of the star collapses completely, compressing all its mass into an infinitely small point, a singularity. In that place, even the laws of physics break down. Space and time cease to exist in any meaningful way, and our ability to describe what is happening simply vanishes. At least, that's the prediction offered by Einstein's theory of general relativity, our most cherished and well-tested theory of gravity. Yet general relativity is not the only player on the cosmic stage. As we've seen, quantum mechanics beautifully explains how white dwarfs and neutron stars resist collapse at the very edge of annihilation. So, it would be premature to abandon quantum theory when two neutron stars collide. The challenge is this: the conflict between general relativity and quantum mechanics has long been recognized. Their descriptions of the universe are fundamentally incompatible. They cannot both be fully correct. One or both of them must be approximations of a deeper, more comprehensive theory, quantum gravity. So, in this grand game to uncover the true nature of reality, which theory will falter first? Interestingly, neutron stars may hold the key to the answer. The 2017 neutron star collision, known as GW70817, marked the first time in history that astronomers observed a single cosmic event emit both gravitational waves and light. This ability to study a single phenomenon using multiple types of signals, such as gravitational waves, electromagnetic radiation, and neutrinos, is known as multi-messenger astronomy. It can be said that the GW70817 event marked the coming of age of multi-messenger astronomy as a mature tool in the astronomer's toolkit. Just 2 seconds after the gravitational waves from GW70817 reached Earth, astronomers also detected a dazzling gamma-ray burst from the same region of the sky. This tiny interval of time allowed scientists to calculate the speed at which gravitational waves traveled toward us. The 2-second delay matched perfectly with the predictions of general relativity, while conflicting with several alternative gravity theories. As a result, GW17087 helped astronomers rule out many competing models of gravity. Another critical test came from a unique system known as PSR J337 plus 750, a triple star system consisting of 2 neutron stars and a white dwarf. Not only do these bodies orbit one another, but the entire trio orbits yet another white dwarf. General relativity predicts the complex gravitational interactions in orbital shapes in such systems with remarkable precision, and so far, it has passed every test. Still, most physicists, when pressed, would admit they believe that general relativity may break down before quantum mechanics does. The reason we haven't yet seen the collapse of general relativity may simply be because we haven't tested it under extreme enough conditions. This is why the core of neutron stars and the quest to discover the correct equation of state have become a fertile hunting ground for new physics. Some quantum gravity theories are only compatible with a narrow range of possible equations of state. So eliminating an equation of state often means eliminating the quantum gravity theory tied to it. In the summer of 2024, astronomers may have made a major breakthrough in this area. A team led by Alessio Marino from the Institute of Space Sciences in Barcelona discovered a group of unusually cold neutron stars. As neutron stars age, they naturally cool down, either by radiating heat directly into space or by emitting neutrinos, which carry away some of the internal energy. The rate of heat loss depends directly on the internal conditions of the neutron star and, critically, on its equation of state. Marino and his team used data from the Chandra X-ray Observatory and XMM Newton, both X-ray space telescopes, to study the radiation from 3 different neutron stars. The hotter a neutron star is, the stronger the X-rays it emits. What they found was astonishing. These 3 neutron stars were 10 to 100 times colder than other neutron stars of similar age. The discrepancy was so large that it immediately ruled out 3/4 of all possible equations of state, and along with them, several quantum gravity theories. This discovery underscores just how crucial neutron stars are to our understanding of the universe. They are, after all, the ultimate laboratories of physics, natural environments that create conditions so extreme they force ordinary matter to behave in extraordinary ways. And so, nearly a century after they were first theorized, neutron stars remain as mysterious and as significant as ever.